Let's go ahead and get started. Just pick up right where we left off on Monday. We were talking about the necessity of doing basic I/O in all of your programs, and as part of the problem-solving process, thinking about what the inputs need to be to your program, what the outputs need to be of your program, and just from a simple sort of testability perspective, the need to be able to look and inspect the variables in our program. And so while these are two of really the first functions you learn as part of the standard C library, printf and scanf, they're pretty critical, and they're pretty critical to get right. Where we left off on Monday is I opened up the documentation page for them, and we saw, if we scroll down there's quite a few different options, quite a number of different ways one can configure those functions in terms of the nature of the input and the output. But I think for now, it's sufficient just to kind of stick with basic defaults for the built-in C data types, your decimal types versus your fractional types versus your strings. Even with that kind of limitation of what you're going to be reading in via scanf and printing out via printf, there's still some things you have to watch out for, even just doing printf. The first thing I noticed, and when I looked at some of the demo programs, a couple of them sort of still worked even with this in not taken into account, is that when you have these conversion specifiers, that percent whatever, in this case, this example, percent %d, for every one of those, both in the scanf and the printf call, that you have within that string, within that text, a block of text between the double quotes, you need to have then, following those double quoted block of text, the comma followed by an equivalent number of arguments afterwards. And based on how that function is written, for better or for worse, the issue is that if you don't have the right number of arguments, it is not technically a compiler error. The function is written printf and scanf in such a way that it does allow you to do things that logically don't make a lot of sense, but are syntactically correct. They're not logically correct. So this example we had here with the print out the number of dogs and number of cats, don't be shocked when this happens to you. You're working on the code and you did a scanf and then you do a printf immediately or soon afterwards to print out those two variables. Now, what I just did just now is I deleted the second of those two variables, the num cats. And the code linter here, the development environment, does actually tell you very subtly that you have done something wrong here logically, or very likely to be wrong logically, but it's pretty subtle, right? I mean, you look at it and now there's a little tiny squiggly line underneath that second %d in the printf, and if you hover over it, says more conversions than data arguments, and that is exactly correct in terms of what it's detecting and what the actual bug is. You have 2% Ds and only one data argument, and they should be matching. But I don't notice it. I type 3 followed by 4. Any idea what that's going to print out? Well, it'd be nice if it printed out error, 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 code is wrong. But for reasons I don't entirely understand, other than we're kind of arbitrarily reading from memory when we don't specify the right number of arguments, it prints out you have 3 dogs and 24 cats. For this example, okay, that's obviously wrong. I typed in 3 and 4 and I got 24 back out. You'll catch it. At least I think you would catch it. Or at least eventually you would catch that error. In the more general case, where the printf is on line, or the scanf, is on line 8, and the printf is based on some derived variable 70 lines later, that's pretty hard to catch, right? When all it was just missing that variable, and then you're doing some arithmetic on the number of dogs, and then it becomes a different variable, and then now you have the task of kind of tracking it all the way back. There's also some rules with regards to how there is white space in both the scanf and printf functions within those double quotes, whether the %d consumes all consecutive white space or if it doesn't. It depends on if it's a character or a string or one of these integer types. There's a couple other caveats with regards to scanf, as we talked about, requires that we provide the address of the variable that we are wanting to overwrite versus the name or the value of the variable we want to print out for all variable types, except for when that variable type actually corresponds to an array. So when you're doing a scanf of a string, it turns out you do not need and should not be using the ampersand symbol there for scanf. But for all your other data types, in fact, you should be. So there's just some ways that you can kind of make mistakes, even with this scanf and printf functions that otherwise are relatively straightforward conceptually. My suggestion for you, as you're getting started with programs that you are writing, you're always going to be reading in data. You're always going to be eventually printing out some results. Have it in part of like your muscle memory when you're typing code of an immediate scanf followed by a printf right afterwards, like this example. Even if for my program, ultimately, I don't need to print out the number of dogs and number of cats, eventually it's total number of animals or something else just based on that. Even so, even when your final output of your program doesn't require you to print out those two variables, just to confirm, before you find yourself tracking down logical errors that could be 40 lines previous in your code, but just to confirm that you've actually done the scanf correctly and your variables that you're typing in as the user are actually have the values that you think they should have and all of your other assumptions flow downhill from that, you should have this scanf printf kind of combo package like this in all the programs you're writing, at least for the near term. And a good chunk of this semester is how I would recommend doing that. It's a little redundant. It's a line of code that maybe eventually you don't need in your programs. Okay, if it turns out you don't need it anymore and it did work correctly, very easy just to comment it out, right? Okay, I wrote that line of code, I actually don't need it. That was very quick to get rid of it, right? To comment it out that it's not there anymore. But again, when you did have potentially a bug in which you weren't actually doing scanf properly, tracking that down is going to be quite difficult if you're not immediately kind of testing you did get the values that you were expecting to be able to get. Otherwise, when doing this, stick with the basics. Still, as part of our problem-solving process, the names of the variables are potentially important so you can understand what the variables are meant to correspond to. And then for C programming at least, the type of our variables is pretty important. Even if it sounds simple in terms of how we're declaring it, such a common cause of bugs in C programs of using the wrong type. Later, as we'll see, allocating memory incorrectly is going to be just an extremely common type of bug that we have to deal with. But we do have to get some comfort level eventually here with deciding what types are appropriate for our program. Again, as we talked about on Monday, you may make that decision and then may later change your mind, and that's okay. But you have to at least think about it as you're writing your program. And because reading an input, reading in some values from the user is very often the very first thing your program is going to be doing, you really can't delay that decision. That's sort of the first thing you have to be thinking about in your program. What are my inputs? What are my outputs? What should I call them? Something reasonable. And what type should they be? I'd like us to just take a couple of minutes and introduce yourself to the person sitting next to you if you haven't done so yet this semester. And consider the following 6 types in C that we talked about on Monday, but you haven't necessarily used them. We talked about how there's some qualifiers on the int data type that allow you to specify whether, for example, you may want to use less than the 32-bit range or more than the 32-bit range for an integer value, as well as a qualifier that specifies whether you want that integer value to be ever interpreted as being negative or whether it always should be a value of 0 or greater. So that's those first 3 types reflecting that in this table here. There's the car data type, which we'll talk more about later on, but for now you can think of this as just a very small integer type. And then we have the data types that allow us to store fractional values. A 32-bit one that's just referred to as float, short for single precision floating point. Maybe if it was called single, that would have been a better name in retrospect. And then double, for double precision floating point, in which we have twice the number of bits of storage, and that allows us a much larger kind of dynamic range for those fractional types. Take just a couple minutes, introduce yourself to the person sitting next to you if you haven't done so already, and try to describe some variable that would need to make use of each of the given types. For you as well, introduce yourself to the people behind you. All right, that was some good sounding discussion. It was all kind of on top of each other, so I couldn't really discern anything specific. But any volunteers? So for the kind of default integer type, any thing that you came up with your group that you'd like to volunteer? What was the name of a variable that you think would be appropriate for an int? Any number within what? Any decimal number, and as I mentioned on Monday, and I think probably should be your default assumption, is that unless you have really good reasons to use unsigned int, short int, unsigned long int, it's a whole number would be the phrase, or a decimal number, int is good to go. So I think that's a valid answer. What about for an unsigned int? What would be a variable that would be useful to have as an unsigned int? Sure. A counting variable, I think, makes perfect sense to have as an unsigned int. Again, I'll go to that caveat that I just said, that if you look at the difference, so that's absolutely correct, but if you look at the difference between an int and an unsigned int here, right, counting people, assuming it'll never be negative people or negative things, that variable type still probably only makes sense to you is if you want that additional higher end range of the unsigned int, because you get that extra kind of half number of representable values, that extra 2 billion values that you can represent there. So then it has to be something for which it's appropriate. Number of people, not number of people on Earth though, right? Because that's not enough anymore, is it, to accurately capture that. Number of people in the Western Hemisphere or something like that. And maybe at that point you have to actually think about that a little bit more, depending on how robust your program needs to be. But here, at least, you have a variable. Thinking about it is probably a sufficient step for now. Whether the solution you come up with is the perfect solution for all scenarios is something different entirely. But having thought about it is probably sufficient. Okay, people, that should be an int. Technically, if there's more than this much, we have a bug in our code. But for now, it's probably good enough. What about a short int? Did anyone come up with an example for that? Sure. Smaller data sizes that you can save on memory. So like maybe you're just doing a poll on your local community, you don't need that many data. The number of people in the department, perhaps, right? I was going to say in the university, but that's kind of borderline, right? It's like 32,000 students or something like that at Iowa State. So that's kind of pushing it there. And so that is correct. It's a valid answer. As I mentioned, and I just want to reiterate again, so maybe we save 2 bytes or 16 bits by doing that, by choosing the short int versus the full blown int. So what, right? Who cares necessarily unless there's some exact reason that that's the case. There are scenarios, before I kind of belittle that concept too much, there are some scenarios where that really does matter, right? We are generating data to be sent as part of a networking protocol over a wired or wireless communication. In those scenarios, the exact format of the number of bits we're sending at least needs to be defined precisely in advance, and every byte might in fact make a difference at the end of the day. And there's going to be an IP port as part of that network description, and 16 bits by spec is going to be enough for that. For all those reasons, we do necessarily want to have that specific data type. But if it's numdogs or number of students on campus, an int is probably also going to work for that. Skipping over car for now, how about for float? Any examples of what we would use float? So for values that you need, the term I would use is just any sort of fractional precision. I'm going to have 2.6 of something. The int is not going to work for that purpose. And we have to think about that from day one in our design process of our programs. But what about float versus double? Understanding that we haven't really talked about it in any detail, other than you can kind of squint at it and see, well, you get a lot more information in a double than you can get in a float, and that's probably sufficient for our understanding for now. What kind of application would maybe need, or variable would need a double precision versus a regular single precision? Sure. And what you will see, absolutely, and what you will see is, while you can't necessarily, just based on this chart that shows the minimum value and the maximum value, well, we can see there's several order of magnitude difference in terms of that size. The other difference is a several equivalent order of magnitude difference in how precise we can get, how much each double can change versus how much each float, that's referred to as like the epsilon value for the data type. How much two floats can be apart is quite a bit larger than how much two doubles can be apart. Oftentimes we see doubles when we have some sort of scientific or even engineering workload where neither of these are exact, right? That there's an infinite amount of values we could potentially have, and there's a trade-off here that there's only a finite number of them we can uniquely represent with this. But more is better. More accuracy is better. So in those scientific and engineering workloads, oftentimes, but by default, we assume, well, let's do double precision floating point because at least it's more accurate than single precision floating point. But a big chunk of those workloads and the programming overhead of those workloads is dealing with issues of precision. Money is an interesting segue, and I don't know how much I want to go into too much detail. For the programs that you write, a float for money is probably good enough. But most, quote unquote, real financial applications do not use floating point values for finance. And the reason's a little bit subtle, but ultimately it's that even though floats have the ability to store fractional values here, there's still a limit to the number of fractional values they can correctly, accurately represent. Just to give an example, a float can't represent 1/3 properly. It'll give you an approximation of 1/3, but won't give you exactly 1/3. And not just that it can't represent some values entirely precisely, it's not always that obvious based on the arithmetic you're doing on values, whether the result you'll get will be mathematically precisely what you want or whether it won't be. So in dealing with money, it's a much more common scenario to have kind of a structured data type that maybe stores dollars and cents and just kind of manually deal with more integer type values for that, where at least you could then represent the number of pennies exactly, as opposed to a float, which would be correct most of the time, but every so often would have a rounding issue and you'd have an incorrect amount of money in an account. For your programs, though, if you want to do a simple supermarket application like we'll have, or float will be good enough for those purposes. But if it was a bank that has certain regulations, then there's different constraints than for an in-class assignment you may have. So remember, ultimately, though, that what is in our memory, let's go back to that abstraction that we're interested in, it's those binary values, those individual bits, those ones and zeros. From an electrical perspective, ultimately, at the end of the day, these are digital binary values, but it's going to ultimately correspond to some sensed voltage value, something physical storing a 1 or a 0 electrically is going to correspond to a 0 or a 1. There's going to be two possible values. We then take these individual 1s and 0s, these binary bits as stored in memory, and we group them together to represent more complex data. So when I talk about the int data type, generally by default being a 32-bit value that we are storing, that's all that that means. We have 32 of these 1s and 0s corresponding to some physical location in our memory, and then they're logically kind of interpreted as corresponding to one thing. Physically, they're adjacent to each other. Logically, in software, we are interpreting them to correspond to one particular thing. There's a fundamental kind of inherent information theory limitation. We'll kind of see this in various different contexts over time, that if you have I bits of storage, you can just uniquely distinguish 2 to the I different distinct values. That is always going to be the case. If I have 4 bits, I can represent 2 to the 4 or 16 unique values. And if I have 32 bits, I can represent 2 to the 32 unique different things. That's true for our ints as it is for our floats. Even though the float is going to take those 32 bits and treat it as some sort of fractional thing versus the int that's going to take those 32 bits and treat it as a decimal thing, ultimately they're both 32-bit types. So there could be 2 to the 32 unique int values in your program, and only 2 to the 32 unique float values in your program, because there's just a fundamental limitation of you have 32 bits or you have I bits in general. The 1s and 0s can be independently flipped across all I of those bits, and you can only have 2 to the I different patterns of those 1s and 0s at the end of the day. Technically, an integer is any non-fractional value in any arbitrary range. But for us, we only have, if we're using 32-bit integers, 2 to the 32 possible integer values. We already kind of talked about that with regards to, is 2 billion enough? Is negative 2 billion enough? But no matter what, no matter how many bits you're going to specify, there's a limit. And you can come up with a value that's larger than that limit. So I try not to set you up with too many scenarios in which you'll get hit by that. But you always have to be aware of that when you're writing a program. That an int is an abstraction of a mathematical concept of all natural numbers, and it's already a trade-off on day one, which is technically this number of this mathematical concept I'm trying to implement in my program could be any arbitrary value. For my program, it can be of that limited set of values. We just have to be aware of it. And C, unlike other programming languages, has a somewhat unique way of dealing with that scenario in which it completely ignores it. And it's an implementation-specific issue when you do have things like overflow or underflow, as we'll see in an example in just a few minutes here. Do you have a question? No, I don't know why I use the value I there. N bits can be used to uniquely distinguish 2 to the n values. So 32 bits can be used to distinguish 2 to the 32 values. And you'd have to kind of draw it out to convince yourself of that, but each of those bits are independently 0 or 1. So there's 2 possibilities for each of those individual bits, and there's n or I or 32 of them. That'll lead to 2 to the 32 possible values you could have. You could write it out, and there's only that many possibilities. Write it out for n equals 3 or 4, not for n equals 32. And you can see how many values those are. For the unsigned integer, 32 bits. This value, which I'm calling 4 billion, but that's an approximation, is 2 to the 32. Why did Windows, back in the 32-bit Windows day, limit you to 4 gigabytes of RAM? Well, it used a 32-bit value to store the address for our variables, and that's as many bytes as you could possibly have. And now you need to use more bytes, more bits to be able to represent more unique values than that. There's also the built-in to the programming spec, the size of operator. We will see other reasons we will want to use this later in this semester, but it is an operator. You can also think of it as a function, but it's a little unique in that it takes as input either the name of a data type or the name of a variable, and it returns back the number of bytes that that variable stores on your particular system. So I talked about how things like int and long, they are defined in the spec, but the way the spec defines them as has to be at least this many bytes, but and can be as many as this many bytes. For your particular system, you may have a different integer than on someone else's different system. That can make writing code that's completely portable across different systems a little bit more challenging than it would otherwise need to be. This semester, our only system is Replit. There'll only be one set of values we'll be running. But when later on, for other reasons, we want to know exactly how big a particular variable is or could be for our system, that size of operator allows us to return that value in terms of number of bytes. I have this example here just to run it. There isn't really much else to do here. It's technically complaining about a data type, but it should print out okay. It's just a printout that says for some of the built-in data types we talked about, size of car equals this, size of short equals this, size of int equals this. When I get this to load, it'll actually run here in just a second, and it will return the number of bytes corresponding to it. If you cared about the number of bits, you could just take that value and multiply it by 8 and get that result there as well. Okay. And it should just print out all those values that we have here. So our car is 1 byte. On this system, our int is 4 bytes. If we were to specify long, that would be a 64-bit or 8-byte integer. We have our float. We have our double, which is 64 bits. This system also allows for a long double, which would be a 128-bit kind of quad precision floating point value. Now, what we also have that you're not going to be required to use this semester, but to the extent we care about our bit precision can be a very helpful thing. There's also, as part of the C standard library, a separate header file and a separate bit of functionality that defines additional types referred to as standard int. And standard int has a set of kind of competing integer types that allow us to be a lot more explicit with regards to how many bits am I allocating for a particular variable. I mentioned the networking scenario. If you were writing networking code, you'd almost certainly want to use standard int. When I use regular old int, I'm kind of at the mercy of that particular system, or I have to check to see how many bytes is that int going to be. I can then instead use standard int. I would argue that this is a typo the way I wrote this. Standard int that defines these additional types that look a little bit more wordy, but what I wrote here was uint8, where you can specify explicitly with the type itself how many bits that integer is going to take, whether it is signed or unsigned. So here I print out size of uint8, T just kind of stands for type, uint, so that's unsigned int, 8 corresponding to 8 bits. When I run that, I should get a value back out of 1 for the number of bytes corresponding to that. If instead I wanted not an unsigned one, but a signed one, and I want a 64-bit one or an 8-byte one, I would then, and there's an equivalent type called int64t, and that would return back out 8. I would argue for your code that if you really want a 64-bit integer, because for your purposes it's necessary for you, then including #include standard int.h using int64t versus long int is probably the way to go, right? Eventually, it's a lot less wordy as well, right? Here's an unsigned 64-bit int. I could do unsigned long every time I want to declare a variable of that type, or I just use uint64t, and it's basically defined to be the same exact thing, but it's kind of more guaranteed to be portable across systems. A little bit easier, I think, ultimately to read. You're not required to use that this semester, but if you do use it, I think your code will be a lot easier to read and understand along the way. So now looking back at our view of memory from the programmer's perspective, now knowing that it's not just an arbitrary collection of bits at the physical layer with some hidden meaning, we know that our memory, based on these C data types, is going to be segmented into individual bytes. None of these data types would ever return 2.5 bytes back out. There are a couple ways we can define things to have fewer than the maximum allowed number of bytes for representation. there usually has to be a really specific need for why you'd have that in your program. So by and large, we can assume we declare a variable, it is a certain number of bytes, an integer number of bytes that we are declaring for it. So that's probably the final view I want you to have of memory. So it's a physical thing. It is a storage. It's our lockers with the names of the variables corresponding to the physical lockers, and the contents being the actual values of those lockers. But ultimately, memory, and certainly the C programmer's view of memory, is it's just one large linear array of bytes. That we have a series of addresses, and we have a series of bytes at those particular addresses. And so our variables that we are declaring are just our way of specifying, I want 1 byte to store this variable. Now I want 2 bytes to store this next variable. Now I want 4 more bytes to store this next variable. And it's up to the compiler and the resulting runtime to determine where exactly in memory those are going to go. But ultimately, our memory is just this big, long range of bytes, of which our variables are taking 1 or more of those bytes at any particular time. And that's, as a programmer, how we should be seeing our variables. In some sense, we shouldn't have to think about memory at all. We declare a variable, we know it goes in memory, that's good enough. When things work, that's sufficient. Later, we have to be a bit more explicit with where we are putting things in memory to get our code to work. But by and large, the compiler is going to be pretty good at deciding where to put things. That now ampersand operator that we've already seen in the context of scanf is doing exactly now what I mentioned, which is, don't give me the value of variable A, which I may still want for other purposes, but right now, don't give me the value of variable A, give me the actual address of where A is stored in memory. Whether that's a physical or virtual location is something that's not super important for us, at least today, but the address. And you can think of that as, in this big long array of memory I have in my system, ampersand A tells me that for when I've run that particular program just now, where did A happen to get placed? When we want to print out addresses, you can use %x because it is just also could be printed as hexadecimal. But as we talked about all the various different options for printf, there's also %p. That stands for printing a pointer, and we'll talk more about pointers as the semester goes on. You can think that as print my address. Print a location in memory, and it formats it nicely in hexadecimal for us. The result you get when you run this example called print pointer may be different than the example I get. There are various rules about where things are going to get placed in memory, but they tend to be very specific to the compiler that we're using, to the operating system that we're using, as well as to all the other applications that happen to be running at one point in time on that particular system. Because we have this big array of memory. That's our programmer's view of what we have here. Gigabytes and gigabytes of memory. But that has to be shared amongst all the programs that are running at any given point in time. We may not think there's anything running on this system at any one point in time, but just to have a runtime environment that allows us to do things like type in commands in the shell requires us to have, it may not give me permissions to see. There's other things running in parallel to what we ourselves may be wanting to be viewing at any one point in time. This is all that it's allowing us to see. I guarantee you it's running other things that it's not giving us permission to see. But right now, just to kind of sit here and wait for me to type in commands, it's running 1, 2, 3, 4, 5, 6 applications. This is kind of the application I just typed in, but still it's running 6 different applications, each of which are using some amount of memory themselves. So where your stuff is actually getting placed, it's going to follow kind of a consistent set of rules, but the actual final location will change depending on the environment you're running it in, what else happens to be going on at any given point in time. So it is oftentimes very difficult to run a piece of code like this and say, yeah, the results are correct or they're wrong. They just are what they are. But we can say we've declared an int A as well as a short b and a c and a d, and we can print out those addresses of where they're actually stored in memory. And that looks kind of maybe scary to you if you haven't played around with hex before. Hexadecimal, we'll talk about it later, is just another way of representing a number that allows it a slightly more compact format. If I wanted to print it as decimal, I could. is just going to be a really big value. It's actually printing it as a negative. So if I want to make sure the topmost bit must be 1, but if I want to have is unsigned value, the location of memory is, let's see here, that's 100,000. Location 1.7 billion ending in 4, and then location 1.7 billion ending in 2. That's the same information that when I print it as hex using %p, but maybe it's a little bit more human readable in some sense there. Any observations when you look at that result when you print it out? There's no wrong observation, but anything comes to mind? Sure.
I have a question. Why did you give A and B a value?
Why didn't I give A and B a value? For this program, I'm not really doing anything with A or B, right? I could. It could have been num cats and num dogs, and I could have added up the values and done scanf. So you're right. In general, you declare a variable, you should probably use it in your program and do something with it. For this program, this demo example, it was just to show that there's an address of the variables you declare. That's all. So if I had done int a equals 3, I have to be careful here. I'm pretty sure it wouldn't change the address it was put at. That's actually a subtle thought. Well, it changed it, but relative to where it was, did not change it. Okay. So first off, that is a different observation, right? I run it, got a different value each time. Let's go back to the unsigned version of it so you can kind of human read what's happening here. Other observations. What else do we see when we look at this? Sure. Need your hand raised, so I pointed at you.
I don't think we declared A for higher address value than B.
To me, yeah, and to me that's interesting. Yeah, absolutely. That's one of the things I wanted you to catch here. I've looked at this a little bit, and C as the programming language specification doesn't require this. There's also kind of a standard executable format that these compilers tend to target, and they do strongly imply that when you allocate your variables, in this case, they're being allocated in a special region of memory referred to as the stack, excuse me, they tend to go backwards in memory. So the first thing you declare is highest location in memory, and then it's working backwards from there. They're off by 2. Why do we think they might be off by 2? Why is 1 plus 2 the other? Because it's just short, and the short's probably only taking 2 bytes. That would be 8. My guess would be, I've been wrong before, they are off by 12. I'm sure there's a good reason for that. Why wasn't it off by 8? Some alignment reason. Another thing, just how about the numbers themselves? This is the only variables that I have in my program, but they don't start at 0. First off, there's whole regions of memory that are reserved by the operating system and other applications. There's this concept called virtual memory, in which the address space the program sees is not necessarily the same as the actual physical wired up addresses of the underlying physical memory. But ultimately, you tend to see addresses that look like that, pretty high locations in memory. I have it commented out. It turns out it makes a very big difference where you declare your variables. I'm inside my main function here. So all of these variables are going to be declared and placed in memory relative to that function. If instead of this A, I wanted to declare a separate A, and we are allowed to do this. We'll talk about reasons why that may or may not be the right thing for you to do in your programs. In this case, it's neither right nor wrong. It's just a different place we're allocating it. Here we're saying B, C, and D are still relative to function main. A is not relative to any function. A is what's referred to in this case as a global variable. So all functions could see variable A for better or for worse. There's upside and downside of doing that. Address of A is going to be totally different than address of B here, right? In fact, it's actually much, much lower, nowhere near where A is, or where B has been allocated in that particular system. Yeah, sure. That's fine. Right, right.
So this isn't rather imagine as if it's like a continuous flow of like this function 1, 2, 3, 4, 5, 6, until maybe a billion or something like that. Is that how imagination is?
I think, well, it is ultimately how it is, and that is how I would want you to be thinking about memory. It is just a continuous set of addresses, and they're addresses for each of the individual bytes. That short took 2 bytes, and that's why there was a 2-byte gap between where B was declared and where A was then declared afterwards. Um, in this case, when we print out the address, the other term you'll see is like the base address or the starting address for that variable, because the variable itself is more than 1 byte, but usually when we say we're printing the address of that integer, it's that first byte address. It's the very first starting point, and technically it's a range of bytes, but we're only printing out the first, the starting location where the very first byte in that integer is located. We know it's 4 total bytes. There's also 3 other addresses where that integer is also partially located. Under the hood, ultimately, we have something physical, our DRAM or our SRAM. Where that physically is going to be laid out really depends on the underlying VLSI implementation. So it's not as simple as it's just this big, long array of ones and zeros of our bytes that we have here. But in terms of our programmer's view of memory, this gets you really, really far. And you don't really have to oftentimes think about it much more deeply than that in terms of where things are located in memory. We need to start talking about expressions next. I know you'll be seeing that in the reading that you're going to be starting on, and it's necessary for the lab as well. Some of this will be intuitive. Other parts I'm going to want us to take our time with and make sure we go slowly and appreciate what makes C a little bit more different than other programming languages with regards to expressions. Otherwise, between now and Friday, what I would like everyone to do, in addition to all the other things you have to do, is look at that next example that we haven't quite gotten to yet, which is the float math example. If you look at that example between now and Friday, and you kind of understand what's happening, Friday's gonna go just fine, and you'll do perfectly fine in terms of understanding this topic. Otherwise, let's leave things here for today. We'll really dive into that on Friday after everyone's had experience with the first day of that lab.